As inferred, today we'll take a moment to discuss how to go about scaling a method so as to improve your efficiency and ultimately decrease your runtime so as to expedite sample throughput. The scope of our presentation today will be primarily just to speak about column dimensions with respect to particle size, and then both the internal diameter and the length, so as to ultimately improve, once again, both your efficiency and your resolution, and ultimately benefiting your sample throughput and runtime. Specifically, we will speak about the effect of particle size towards efficiency, how to then go about adjusting the flow rate for the intended internal diameter of your column, and then finally how to put all of that together when optimizing the particle size, flow rate, and column dimensions all at once. From there, we will then be able to pivot and discuss how to implement all of this while working within the limitations of whatever instrumentation you may have available to you in the lab. Later on, when we have a moment for questions, we can perhaps elaborate on these topics as they pertain to ideas regarding stationary phase selectivity, or perhaps even scaling upwards towards preparative purification methods. So when we talk about the benefits of scaling an HPLC method to UHPLC, we are speaking to primarily to improvements towards efficiency, resolution, and throughput. By efficiency, we are specifically talking about generating sharper peaks. So with sharper peaks, you certainly improve your sensitivity, and you also benefit the resolution that can be attained during the method, specifically the quality of the separation that distinguishes one peak from any neighboring peaks. Once you have improved your peak efficiency and resolution to a certain point, it's not necessary to have such a long separation runtime. So you can then take measures to shorten the runtime of your method while preserving your desired resolution. As many of you probably know, when working with smaller particles, this will generate higher back pressures. And so whenever considerations are made towards scaling a method down towards UHPLC, you do need to take into account the back pressure limitations of your instrument. But thankfully, there are many ways to work around that, and we will discuss some of those tools, primarily in the form of core shell particles. Efficiency and sensitivity. Once again, we are speaking to achieving sharper peaks. Ultimately, this will improve your ability to work towards lower limits of quantitation and perhaps even lower limits of detection. And shown here is an example of that. This is a particular example that we will refer to a few times throughout this presentation as we delve deeper and deeper into the details therein. For now, though, what we are looking at are an overlay of two chromatograms that were performed with the same instrument conditions, the same sample, and the same column dimensions with respect to the length and the internal diameter. The only difference being the particle size. The blue chromatogram representing a 5-micron particle size, while the red chromatogram represents a much smaller 1.6 micron particle size. And again, it's also important to point out that we are working with the same particle morphology and stationary phase, specifically fully porous particles with a polar C18 phase. And what we see as a result are indeed sharper peaks generated by the smaller particle size. And you can even see how this will be a benefit towards resolution, which we will explore in more depth in just a moment. Once you've established those sharper peaks, you, as hinted earlier, you don't need as long of a runtime. And so Here are two chromatograms, which we will explore later, that exhibits the same resolution within a sample, but as you can see, the top chromatogram was achieved within a 63-minute runtime using a 250 by 4.6 column with 5 micron particles, as compared with the bottom chromatogram achieved in a much shorter 14-minute runtime using only a 50 by 2.1 packed with 1.6 micron particles. So the point here is, once again, a surplus of resolution then allows you the flexibility to shorten your column dimensions so as to achieve shorter runtimes while preserving resolution. Once again, though, we need to be mindful of instrument considerations, specifically when working within back pressure limitations. And here is where core shell particles allow one to pursue UHPLC levels of efficiency and resolution, as well as runtime, while avoiding the back pressures that are typically associated with smaller particles. Here's an example that we will explore later on, in which we compare the same sample, same instrument conditions and column dimensions, but with the use of either fully porous Luna C18-2 particles or core shell kinetics C18 particles. And again, the particle size is actually the same in these two examples, the only difference being the Luna particles are fully porous, while the kinetics particles are core shell. And we can see where the kinetics provides benefits with respect to both sensitivity as well as a shorter runtime. Higher sensitivity, shorter runtime. And so now let's start diving into those details as to how particle size begets a certain level of peak efficiency, which is to say, why do smaller particles generate sharper peaks? We need to be mindful of the length of the pore pathways that bore their way through the particles. In short, the larger the particle, the longer the pore that bores its way through that particle. And perhaps it will benefit us to take a further step back and ask ourselves, what is it that we're really looking at when we see a peak? The peaks actually represent what we call an analyte band, which is the grouping of all of the actual molecules associated with a specific analyte. We want that analyte band, that cluster of molecules for one specific analyte, to be as consolidated as possible so as to generate a sharp peak once that band passes through the detector. Reality, though, is such that as that band migrates through an HPLC column, it will broaden a little bit as some molecules move a little faster than others. We need to be mindful of the rate at which a molecule travels when it actually partitions into and out of the pores for each particle. And we also need to be mindful of how molecules move about within the interstitial spaces between particles. Larger particles generate both longer pore lengths as well as larger volumes of interstitial space. Smaller particles, however, are more apt to keep our analyte band tight and compact and consolidated so as to ultimately generate peaks that are sharper, taller, narrower, and more efficient. What we are doing is we are consolidating all those molecules into a very narrow band such that the peak area then must be manifested as a narrower and taller peak. Peak area is always going to be proportional to the amount of analyte that you actually load onto a column. The question is whether that area is spread out in the form of a broad peak or is narrow, sharp, and tall so as to generate a more efficient peak. So let's first take a look at how we see improvements to our sensitivity. Once again, same sample, same particle morphology, same column dimensions, same instrument conditions. We were just comparing 5-micron fully porous Gemini C18 particles with 3-micron particles from the Gemini C18 particle morphology. And we see we have sharper peaks that generated greater sensitivity, specifically taking a look at our UV-Vis values of 630 compared on the 3-micron particles compared with 490. We also see sharper resolution between peaks 4 and 5 when using the 3-micron particle size. Keep in mind that retention times are the same. That is because we are using the same particle morphology, which is to say, in both instances, we are using Gemini C18, but we see sharper peaks as a result of using the smaller particle size. The smaller particle size actually helps us to separate out challenging impurities. In this case, we are comparing 5-micron particles with a 1.6-micron particle, and we actually were able to achieve resolution of a problematic impurity. Again, same sample, same instrument conditions, same column dimensions, same morphology with respect to linear omega PSC18. In addition to achieving that sharper resolution, once again, take note of the improvement towards sensitivity. And so now is where we start to run into those questions about what flow rate should be associated with each particle size. And when we speak about flow rate, it's important to take a step back and recognize that flow rate is ultimately going to work in tandem with the dimensions of your column to determine the linear velocity. The linear velocity is the rate at which your analyte band will travel along the length of the column. It is important to scale your flow rate proportionally with your internal diameter so as to achieve specific values for linear velocity. Each particle size works best with a certain range of linear velocity. Admittedly, smaller particles afford a much broader range for optimal rates of linear velocity, which we'll explore now. We can see here that with a chromatogram that we saw earlier, that when we apply the same instrument conditions, we see that in addition to the more efficient and symmetrical peaks with the 1.6 micron particles, we also see a bit of tailing exhibited by the 5-micron particle. Be mindful that we are using a 0.4 milliliters a minute flow rate through a 50 by 2.1 column. That's a pretty aggressive flow rate for that particular internal diameter. And as a result, that is why we see the tailing exhibited by the 5-micron particle size. What's happening when we use specific linear velocities through a given column? Here is where the Van Diemter equation and corresponding Van Diemter plot come into play. This equation can be summed up with 3 primary terms, those being our eddy diffusion term, longitudinal diffusion, and finally, mass transfer. Colloquially, these are referred to as the A, B, and C terms. But now is where it's appropriate to delve into what each of these actually represent in terms of what is happening inside of your column. Eddy diffusion is just the lateral movement of analyte molecules along the length of your column. And it's dependent on this is dependent on the particle morphology, independent of column dimensions, and it's actually independent of flow rate. It's strictly dependent on particle morphology, primarily particle size, but also just the quality of the consistency of the particle size. Smaller particles generally lend themselves to more consistent particle size, and ultimately more consistent flow paths of your analyte molecules through the column so as to minimize such effects as laminar flow and that distension of the cross-sectional flow path of the analyte band through the column. So in short, smaller particles, less contribution from eddy diffusion. The next contribution towards that can affect your the sharpness of your peaks is longitudinal diffusion. Longitudinal diffusion is a reference to the dispersion of analytes within the mobile phase. And this is dependent on flow rate. Specifically, it is indirectly proportional to the flow rate. The faster the flow rate, the less contribution from longitudinal diffusion. Faster flow rate, smaller contribution of longitudinal diffusion. And if you can imagine, as your analyte band migrates through the column, you can often just imagine it as a group of school kids that are just running about. As long as you have an authoritarian teacher walking behind those kids and keeping them in line at a fast flow rate, they'll stay orderly. But if you let them just stand around, pretty soon they're going to run amok. So with respect to the means by which an analyte band is ushered through the column, we are a faster flow rate keeps that analyte band nice and compact and prevents our molecules from diffusing about on their own accord. Finally, we have mass transfer. Mass transfer is a reference to the actual partitioning of analytes into the pores and ultimately the stationary phase that characterizes the particles of a column. So, with mass transfer, we are actually, the contribution of mass transfer towards broader peaks is actually directly proportional to flow rate. With mass transfer, we need to be mindful of allowing molecules an opportune moment to partition into and out of the particles, such that when one molecule is traveling through a pore and another molecule is traveling around a particle, we want to make sure that they stay together with respect to the length that they've both traversed along the length of the column. And here's where I need to apologize and just once again take a step back and say that when we are talking about the Van Deemter plot and the Van Deemter equation, this is one means by which to represent the efficiency of your analyte band. Once again, how sharp is your peak? When we speak about column efficiency, we often refer to it as plates, and that is just it's a term borrowed from the distillation industry, where they literally use plates along a column to distinguish, to collect distillate that has condensed. The more plates present, the finer the partitions from one component within that distillate to the other. And so within chromatography, we borrow that term and refer to it as theoretical plates. And so you can think of a theoretical plate as an interaction between the analyte and the stationary phase. Within a set column, the more plates you have, the more theoretical plates you would have, the shorter the distance between each of those theoretical plates. We refer to that distance as the height equivalent of theoretical plates, HETP, as graphed right here. We want the most plates possible, highest level of efficiency. Conversely, we want the smallest theoretical plate height, as demonstrated right here on this graph. So to elaborate a little more, what we need to be mindful of is, once again, the contribution of our eddy diffusion. Keep that as minimal as possible, using as small particle size as we can get away with. Longitudinal diffusion, this will decrease based on increasing flow rate, But as you increase that flow rate, you actually increase the opportunity for band broadening due to, as a result of the C term, which is our mass transfer term. We need to make sure that our NOI band stays compact as some of those molecules partition into and out of particles while other molecules travel around those particles. Now we can return to explore this graph, these overlaid chromatograms, and we can get a better idea of why those 5-micron particles exhibited some peak tailing. So specifically, that flow rate was very aggressive for a 50 by 2.1 millimeter column. As a result, it generated band broadening as our NI bands had to negotiate partitioning into and out of the pores associated with the larger 5-micron particle size. Conversely, with the 1.6 micron particle size, those pore lengths were very short, such that we saw very expedient rates of mass transfer of each molecule into and out of the particle, ultimately begetting sharper, narrower, more symmetrical peaks. And so now we start running into, well, once we've increased that resolution, we have a chance to, and we have more resolution than we really need, we can afford to shorten the column so as to return to our original level of resolution while also achieving a much shorter flow rate. So just be mindful, though, that when we speak of resolution, and specifically when we speak of theoretical plates are referred to as the N term, oftentimes when speaking of resolution. And, there's a certain extent to which improving your resolution or improving your theoretical plates will ultimately both improve your resolution and allow for shorter runtimes. So there is always opportunity also to consider the selectivity, which is actually a function of your choice of stationary phase, in addition to such method parameters as pH and such within your mobile phase. When we talk about particle size, we are specifically addressing the efficiency term within the broader resolution equation. Before we can explore how to go about migrating from the upper chromatogram displayed here to the lower chromatogram, it's important to speak about not only how to go about scaling your flow rate for a narrower internal diameter, but also just why we do it. Oftentimes when scaling a method, it is with the intention of performing mass spec detection, mass spectroscopy detection. And so what's important here is to note that when you're using a wider internal diameter, you are introducing a much larger volume of eluent from the column into the mass spec ion source. And this ultimately presents challenges with respect to the sensitivity towards your actual analyte that is being introduced within that large volume of eluent. Certainly, you could just increase the mass load onto the column, but then you're once again running into complications with respect to just the upper limitations of what your mass spec detector can handle. So a narrower internal diameter just mitigates all those challenges, such that you're introducing a smaller overall volume continuously into your mass spec ion source, and your analyte has a better chance of standing out, so as to ultimately be directed on into the mass analyzer component of your mass spec, be it a quadrupole or otherwise. Smaller ID also gives you a chance just to conserve mobile phase overall, but really we are being mindful of improving sensitivity by mitigating opportunity for ion suppression that would otherwise occur with a large volume of element going into the mass spec instrument. When you when you want to go about scaling your flow rate, be mindful of the internal diameter, and you can actually just use a simple scaling factor of just simply it's the ratio of the diameter to which you are scaling divided by the diameter of the column from which you are scaling, and then just be sure to square that ratio before multiplying it by your flow rate. You could also use that same scaling factor to, if you want to scale other parameters such as your injection volume or the amount of sample mass that you are loading onto the column. But when we do this with respect to flow rate, ultimately this is intended to preserve the linear velocity along the length of your column. As long as you preserve your linear velocity, this also allows you not only to transfer isocratic methods, but also gradient methods using the same time points of your gradients, and during which you will achieve these same retention times. And we'll see an example of this in a moment. Shown here is a visual representation of scaling that has been performed correctly. This has been performed properly. We can see just visually how we need to lower the flow rate, which is volume over units time, introduced into the column to preserve the rate at which we travel along the length of the column. In this example, it's done correctly. We've preserved our linear velocity of about 6 centimeters a minute. But if we were to keep the same flow rate when migrating from a 4.6 millimeter ID down to a 2.1, this is what happens. If we kept that same flow rate of 1 milliliter a minute, we would end up generating a very aggressive linear velocity upon using a narrower internal diameter. Ultimately, this will this will certainly disrupt your peak shape in addition to your resolution, and it will generate very unexpected retention times. And then on a more pragmatic end of the scale, it will just simply generate a very high back pressure and probably result in an instrument shutdown. When scaling is performed correctly, to begin with, we see the preservation of where you would expect each retention time to occur for each analyte. Shown here, we are looking at the same sample, same mobile phases. I got to be careful not to say same instrument conditions, same mobile phases. And then with respect to the column, the same particle size, same length of column, the only difference being we're comparing a 4.6 millimeter ID with a 3.0 millimeter ID. We've scaled the flow rate correctly so as to reasonably conserve the linear velocity in this example. This also works when working with core shell particles, but be mindful that we need to preserve the particle morphology when going about this. If you're beginning with a core shell particle, continue using a core shell particle. If you're beginning with a fully porous particle, continue using a fully porous particle when you pursue this. And so in this example, we've preserved the linear velocity almost exactly. And once again, same particle size and morphology, the same sample, same mobile phases. Difference being a higher flow rate, 2.35 milliliters a minute when using a 4.6 millimeter ID, compared with a 0.49 milliliters a minute with the 2.1. We can actually take this a step further and observe and take a look at the quality of the chromatograms here. That flow rate, 2.35, should strike you as a little odd for a 4.6 millimeter ID column, and it is odd. And what we actually see are some broad peaks, when we compare it with the 2.1 millimeter ID. So what is happening here is that with the wider ID, we see an opportunity for a more distended laminar flow to occur. A narrower ID kind of constricts the cross-sectional area such that we don't see as much of a laminar flow. As a result, we see sharper peaks due to a more symmetrical analyte band that passes through the detector. With the wider 4.6 millimeter ID, this aggressive flow rate, we're going to see some laminar flow contribution to the analyte band, which resulted in the broader peaks that you see there. Finally, with an example of applying proper scaling to a gradient, we here in this example we have transitioned from a 50 by 2.1 analytical column all the way down to a 50 by 0.3 millimeter micro LC column. The linear velocity has been preserved. The flow rate has been scaled proportionally. And you'll see that, one, we are maintaining the same time points for the gradient, achieving more or less the same retention times, comparable retention times. But I also want to draw your attention to sensitivity. And this goes back to another reason as to why we scale. Scale in a method will improve your sensitivity. And specifically, when using a mass spec, in this case, when we scale down to a narrower internal diameter, we are minimizing the contributions of ion suppression from the mobile phase, allowing our analytes to stand out more. And in this instance, we were able to load a smaller sample mass onto the narrower 0.53 millimeter ID column. This is the chromatogram on the bottom. And yet with that smaller sample mass, we achieve a comparable levels of sensitivity. So almost the same level of ion counts as we did when injecting a larger sample load onto the 50 by 2.1 millimeter ID. So we have preserved the time points of our gradients, and we have increased our sensitivity upon transitioning to that 50 by 0.3 millimeter column. And so now we can put all this together. We can change our particle size and change our column dimensions at the same time so as to scale a method with the intent of increasing sensitivity, preserving our resolution, or perhaps just simply improving our resolution, and then also accelerating the throughput and turnaround time, which has the additional benefit of reducing the solvent consumption during a method. We do want to go about this step by step, but thankfully now we have the tools to do it. We'll begin by addressing the particle size, after which we will address the linear velocity with respect to with respect to the particle size that we're choosing, and then we can go about scaling it with respect to both a shorter column when speaking to the length of the column, and of course, we'll address the ID of the column. So here's the method with which we're beginning. It's not an ideal method, but it got the job done. I'm sure many of you can empathize with that sentiment. We've all been there. So in this original method, it's 63 minutes long, and we are using a 250 by 4.6 millimeter column packed with 5 micron particles. The flow rate is aggressive, admittedly, for this method, but had we used a more ideal flow rate for this column, we perhaps would be looking at a 90-minute or perhaps even a 2-hour method. So 2 milliliters a minute generate, for a 63-minute method here. Let's first address that particle size. If we scale down to a 3-micron particle size, now and we'll still continue to work with the 2 milliliter a minute flow rate. Now the linear velocity is more suitable for the particle size. Upon using a smaller particle size, we generated sharper peaks, which improved the resolution to the point where we could then consider using a shorter column. This returns us to the same resolution with which we began, but it does so with a 42-minute method. But we can take this a step further. We use the smaller particle to generate sharper peaks, and with those sharper peaks, we could then afford to use a shorter column. Let's see what happens when we use an even smaller particle size. And in this example, we're using a 1.6 micron particle size. But then we had to take the additional step of using a narrower internal diameter. Generally, when working with smaller particles, you do want to be mindful of the internal diameter. One, it's just easier to pack a narrower particle size when using particularly small particles. But also, more importantly, this goes back to the point I made earlier regarding laminar flow. With a smaller particle size and when working with a narrower ID, you preserve the symmetry of your analyte band. So upon switching to a 50 by 2.1 millimeter ID column, we needed to scale our flow rate such that a flow rate of 0.5 milliliters a minute has a corresponding linear velocity of 14.4 centimeters a second. Previously, we're working with linear velocities of about 12 centimeters a second. The small particles generated even sharper peaks, so as to then allow for us to use a shorter column, in this case 50 millimeters, and all the while, we're improving our sensitivity. So here is a comparison of the method with which we began with the final method to which we scaled. So we have reduced our runtime from 63 minutes down to 14 minutes. We are using a flow rate for which the corresponding linear velocity is suitable for the particles so as to ensure symmetrical peaks. And keep in mind, 14-minute methods with a 0.5 milliliter a minute flow rate will certainly work towards conserving your mobile phase. And so all of that is fantastic if your instrument can handle the back pressure that is commonly associated, the higher back pressure that is commonly associated with smaller particles. If you're working within your limited back pressures, or perhaps you just want to keep back pressure on the lower end of things, just out of precaution, then core shell particles are a fantastic alternative both to achieve UHPLC results. Specifically, core shell particles will replicate the efficiency of smaller, fully porous particles. And in doing so, by using a larger core shell particle, you also lower the back pressure that will be generated during your analysis. So now we have a chance to revisit 2 chromatograms that we saw earlier. When using core shell particles, you don't necessarily have to use smaller particle sizes. You can use the same particle sizes with which we are accustomed and achieve sharper peaks within shorter runtimes. But how does this actually happen? When we generate a core shell particle, we actually use a non-porous silica core onto which we then apply porous silica. Specifically, the porous silica is grafted onto the smaller non-porous silica bead. The resulting pore channels are, feature a shorter length than the pore channels that bore through a fully porous particle of the same size. To walk through that visually, we are looking at two particles that are the same size, and yet you can see how the fully porous particle features longer pathways through the particle when compared with a core shell particle of the same size. Those shorter pore pathways generate faster rates of mass transfer so as to ultimately generate sharper peaks. And yet we accomplish this without having to resort to smaller particles, thus preventing any increases in back pressure. And so when you use a 5-micron core shell particle, this actually replicates the efficiency of a 3-micron fully porous particle. And then when you do want to delve into the realm of UHPLC performance, a 2.6-micron core shell particle actually replicates the performance of a 1.7-micron fully porous particle. The only caveats of which to be mindful are that fully porous particles do lend themselves to higher sample loading, and so as a result, it does work out when you want to when you do have ambitions of scaling up to preparative purification, for which fully porous particles are often preferred. But on the flip side, core shell particles are a fantastic means by which to mitigate back pressure that would otherwise be generated by smaller fully porous particles. So if your concern is sample load, fully porous particles are a great option. If your concern is minimizing any wear and tear on the pumps for your instrument, then core shell particles are a fantastic choice. And then as for returning to what we had discussed earlier with respect to the Van Diemter plot, just be mindful that when we speak about core shell particles, it's more of a representative particle size as it pertains to the Van Diemter plot. So once again, 5-micron core shell particles are comparable to 3-micron fully porous particles. Likewise, 2.6-micron core shell particles are comparable to 1.7-micron fully porous particles. And as we see here, we see a comparison of a Kinetics 2.6 C18 with a Luna 3-micron C18. In this instance, 2.6 micron is comparable in particle size to 3 micron, but we of course see much sharper peaks generated by the core shell particles, the Kinetics core shell particles, when compared with the fully porous Luna 3 micron particles. We also see shorter runtime, and once again, as a result of those sharper peaks, greater sensitivity. When you want to, if you need a reference when first approaching method scaling, we do have a fantastic web tool through our website that can guide you along. Just be mindful of whether you're working with a gradient or an isocratic method. It can address both, but this will also give you an opportunity to not only evaluate different column dimensions, but actually pivot between fully porous and core shell particles. Just be mindful of the goals of your scaling, of your method scaling, and to keep things practical with respect to the instrumentation that you have on hand. And so when I speak about goals, that just refers to just how fast, are you looking towards improvements of sensitivity, Are you just trying to decrease your runtime? And are you open to pivoting between fully porous and coarse shell particles? The web tool is actually fantastic when applied towards one of the examples that we use today, specifically when comparing these two methods that I have displayed. When we migrated from that Lunar Omega 3 micron C18 down to the Lunar Omega 1.6 micron C18, here are the actual experimental conditions that we used for both of these chromatograms. Be mindful of the gradient tables in particular. And now we're going to take, so we see that we've preserved our resolution, when migrating from one to the next. But we are now going to see how those gradient tables performed with respect to the web tool. Here's a comparison of the web tool compared with the actual gradient tables that we used. So keep in mind that as with any online tool or online calculator, they are fantastic references, but you can see here that with some of the numbers generated, for example, with some of the recommendations for the times, when we scaled down to the 1.6 micron particles, the recommendations for times were 0.37 minutes, 10.37 minutes. One, keep it practical, and simpler is better. So 0.5, 10.5 minutes. But also just be mindful of other parameters within your instrument, specifically the dwell volume of any tubing. When scaling down, you want to shorten the length of your tubing as much as possible so as to minimize dwell volume. As your analyte band travels through the tubing, that's just more opportunity for the analyte band to broaden through longitudinal diffusion. So just be mindful of that. And but otherwise, this particular web tool is a fantastic reference as you navigate all the variables therein when it comes to method scaling. And so this brings me to my conclusion. Just be mindful that smaller particles will generate higher rates of efficiency, ultimately generating greater resolution. As a result, smaller particles are a means by which to improve throughput by allowing for shorter columns and certainly faster linear velocities. But as you go about scaling, keep in mind the relationship between flow rate and the internal diameter of your column. And then also always be mindful of the option of using core cell particles so as to achieve your UHPLC goals without necessarily generating excessively high back pressure. With that, thank you very much for your time. You can reach myself and my teammates online through the chat feature on our website, and we can answer any of your questions with regards to pursuing method scaling and how to choose the appropriate products with which to reach the goals of your analysis. So once again, thank you very much, and I wish everyone well.